Now, we previously derived the expressions for the voltages separately of the inductor, the capacitor, and the resistor. The total voltage across the combination, which would have to equal the driving voltage of the circuit, is going to be what? Can you write down the expression for the total voltage? We want to write that expression down and then relate it to our phasor picture. Okay, hopefully you wrote it down. If you write it down, it looks like this. Your resistance voltage is just the resistance times your I max sine of omega t. Recall that our premise was that your current function is just I max sine of omega t. And that implies everything that we've done so far. Okay, so there's your current. Now, we're using the sine instead of the cosine. That's a little inconsistent, whereas I tried to say inconsistent. That would imply that we're projecting I onto the vertical axis here to get our current function. And really, I probably should have been using cosine throughout, but it really makes no difference in the ultimate result that we have here. Okay, so that actually does make a difference in this picture up here. So you might think about how you would revise all this if this was a cosine. All the phase relationships would be identical, and it would be a good exercise for you to understand the entire development. In any case, what we get is this voltage function. And actually these functions would be all projecting on the vertical axis here. Again, you should think through that and fix it. I'll probably do a quick fix after you've had an opportunity to at least do that. Okay, under this assumption, here are our three functions. We add them up. Now, we can add the two cosine functions, and we can, well, we could factor out the I max. It turns out I didn't. But we have the sine function here that corresponds to the resistance, which is in phase with the current. And we have this function here, the difference of the two reactances, the capacitive and inductive reactances, and that times the cosine of omega t. What's the magnitude of that function? What's the magnitude of your voltage? What's the magnitude of the function you get when you have this? And I suppose what I really mean is what's the magnitude of your maximum voltage here? Actually, no, just the magnitude of this voltage vector. Okay. Go ahead and find the magnitude of that voltage vector. I'll be back in a second. I'm going to write down the result and then explain it. In addition to that bad idea of using the sign here, I neglected to write down the terminology. The circuit impedance is going to be your R squared plus XL minus XC quantity squared. And phi is called the phase of your velocity, your voltage function V of t relative to I of t. So if V of t is in front of I of t, then it's a positive phase. V of t behind I of t, it's a negative phase. And you should again think about what that means about the looking for words here. The graph you get, your graph of I of t versus V of t. I had a better set of words, but they never came out. Okay. Also down here, I wrote down these two expressions, which are the expressions for the impedance, but of course I should have written times I max in both cases. I don't have room to write them both, so I'm going to remove this and just write the I max here, and you understand that the XL minus XC is the same as omega L minus 1 over omega C. Okay, I've made that modification. Also, I should have written this as magnitude of V max, your maximum voltage. Clearly, the voltage of the source, the voltage across the circuit, is going to be variable. You're going to have oscillating voltage. It's going to be a sine or cosine function. So there you have it. Now in another video, I'm going to quickly go through and make the changes we need to make to really resolve everything with this picture for a current function that's driven by a cosine rather than a sine. Okay, now that might have given you a little bit of trouble. Remember, we have formulas for the sine of alpha plus beta and the cosine of alpha plus beta. Those sum of angle formulas can be used with this to determine the magnitude of this quantity. An easier and equivalent analysis puts the coefficient of the sine on the one side of a right triangle, the coefficient of the cosine on another side of the right triangle. And you can see that right triangle up here where you have the cosine function. You'll be taking the cosine of this arrow, and the sine is going to correspond to this arrow here, and the angle is going to be this angle up here, and I'm kind of pointing vaguely. You can work out the details of it. I'm not going to go into that much detail. The right triangle is straightforward enough. Now I've used XL and XC instead of omega L and 1 over omega C, but those are our inductive and capacitive reactances, and they could be written omega L minus 1 over omega C here. Now, we just use the Pythagorean theorem, and we find that the hypotenuse of this triangle, which is going to be the magnitude of this vector, is r squared plus xl minus xc quantity squared multiplied by I max. This is your equivalent reactance, and we'll talk about that in a second. This is what you would multiply by the current to get this voltage. In this case, remember that XL minus XC, your 1 over omega L minus 1 over omega C, is a fairly short vector, and your R was short to start with, so you get a pretty small reactance, a pretty small product when you multiply it by I max, giving you a voltage that's smaller than the instantaneous voltage through, or the maximum voltage through any of the circuit elements. They're kind of interfering with each other. And you also have this phase angle phi, which is the arctangent of this over this. In other words, the tangent of phi is the opposite side over the adjacent. And you get tangent of phi is r over xl minus xc. Now, this xl minus xc could be positive or negative. In this case, it's negative. You can adjust your thinking a little bit. You can make these all vectors and so forth. But it all works out. The tangent of phi is going to work out if you use the negative here. Whether this is positive or negative, if you take the tangent, you're going to get a positive tangent if XL is bigger than XC, a negative tangent if XL is less than XC, giving you either a positive angle phi, which would have the resultant velocity vector on this side of the current, or, as in this case, a negative value of phi, which puts the did I say velocity vector? The voltage vector on this side of phi. So that, okay, phi is the inverse tangent of r over xl minus xc, which is the inverse tangent of r over quantity omega L minus 1 over omega C. Again, let's write out the expression for the voltage. I'm going to pause and do that. Okay, here's our voltage function, and as a bonus, we get our function for the phase angle phi between the current and the resultant velocity vector. Now, I'm going to draw a picture of that. You should try to draw a picture that just shows the current in the velocity vector without the resistance voltage vector, the inductance voltage vector, and the capacitor voltage vector. So here we have our I of t vector, our v of t vector, and the angle phi, corresponding kind of to the pictures that we have here. Once more, this vector could be longer or shorter. It depends on the value of omega L, and the relative length of this vector depends on the value of 1 over omega C. And the R vector, of course, depends on the magnitude of the, depends on the resistance. It is the maximum current times the resistance. As I've said, this whole analysis needs to be modified just slightly. I've got to change the sine function here to a cosine function, but everything still works out exactly the same. It just makes better sense of the picture if I have the current being the cosine of omega t, so that, as I've depicted it, the current really is the projection on the x-axis. We could equally well use the projection on the y-axis. We're just more used to using the projection on the x-axis, and that's really the way I've referred to it throughout.